Assalamualaikum warahmatullahi wabarakatuh. We are from Group 5 and this is our digital communication system implemented in Wokwi using ESP32. So the system combines register encoding, AFSK modulation and also SO checksum verification to transmit and verify the data. A potentiometer is used to simulate channel noise while the OLED and LEDs display the communication status and error detection results. So next I will pass to Auni to explain the encoding process.
Okay, first our group data enable is 0011 and then first an XOR checksum is calculated and will be added to the data and then it will produce the packet 00110. It will produce the packet 00110 and then from the packet 00110 we will do the Manchester encoding where the binary 1 is represented as 10 and the binary 0 is represented as 01, and that's how the packet will be converted into 01, 01, 10, 10 and 01 before it will be transmitted. And next.
So now I will explain about how the BFSK works in this simulation. So basically, for the bit 0, the frequency assigned is 900 Hz, and for bit 1, the frequency assigned is 2800 Hz. So where the bit 0 period is 1111 microsecond, and the half period is 555 second. While the bit 1 have a total period of 357 microsecond and half period of 178.5 microsecond. So how the BFSK functioning in giving the output? So the output will have decision threshold where the half period of bit 1 and bit 0 will sum up and divide by 2 and get 367. If the measured pulse is shorter than it, so it will decode it as binary 1, and if it is longer than the decision threshold, it will decode it as 0. So I will explain the BFSK waveform as well. So basically how the BFSK waveform works. So as we can see, if the graph rapidly change between high and low, it shows the binary 1, represents the binary 1, where it alternates so fast. While if it alternates so slow, have gap between each other of the waveform, it shows that the output is binary 0. So that's all from me. Thank you.
So at the receiver side, the FSK signal is demodulated and Manchester is decoded. So the checksum value is recalculated and compared with the received checksum. If the values match, the OLED displays pass and the red LED remains off. If the green LEDs display the received data bits, while the yellow LED indicates synchronization during transmission.
Okay, so now I will perform the stress test to investigate the effect of noise on the communication system. So we use the potentiometer to introduce the timing jitter that simulate AWG and noise. So as you can see, at low noise levels, the received data is recovered correctly and the checksum show pass successfully. As the noise level increase, the BFSK timing become distort and decoding error begin to occur. So when the noise reach around 263 millisecond and above, the receiver can no longer recover the signal correctly. So the checksum mismatch, and as you can see at the OLED display fail and the red LED turning on, so it indicate that transmission error have been detected. Okay, so now I will show the graph of noise versus checksum failure. Okay, so in this graph, 0 means a checksum pass and 1 means checksum fail. So as you can see, at 0 millisecond and 150 millisecond, the checksum state is 0, which means the transmission passed successfully. And starting from around 263 millisecond, the checksum failure begin to occur. So the graph start rising to 1 and 300 millisecond, the checksum remain 1, so meaning that transmission fail. So that's all. So in conclusion, the Manchester encoding, BFSK modulation, and XOR checksum verification, it improved the communication reliability and help detect error under noisy channel condition. But however, when the noise become too high, the corrupted BFSK timing prevent accurate signal recovery. So it result the checksum to fail and trigger the red LED. Okay, thank you.